teach classes related to software and statistics. And one of the topics I teach is survival analysis. So let's get into that. If you joined the Slack channel, you will find a link there that goes to this page, which is the home page for the tutorial. And you will find two things there. One of them is this link, which will be my slides. I'll be presenting them, but if you have the slides up on your screen, that can be useful. If you get ahead or behind, you can catch up. And then we're going to work in 2 Jupyter notebooks today. The notebooks run on Colab, so you don't need to install anything. When we get to the notebooks, you can come back to this page and click on the links, or there are also links in the slides as we go along. So I'm going to start here in the slides. I'll present for a few minutes, and then we'll get into the first notebook. If you have any technical problems, let us know on Slack. That's the best place to put questions. Please don't use the Zoom chat just because there are too many channels to keep track of. And I'll pause every once in a while to check and see if we have questions and answer things. If you didn't get the link on Slack, you can also use this URL, alandowney.com/SAP for survival analysis in Python. And that will take you to the same page where, again, you'll get the slides and the notebooks. So let's get into it. Survival analysis is vastly underappreciated. And I have to say that on my first slide because I tweeted about this workshop a couple of weeks ago. And the first response I got was from Anurag, who said, survival analysis is vastly underappreciated. And I decided that that has to be my first slide. So that's why it was the first slide. And let me explain what I mean by that. If you do statistics major, you might take a class on survival analysis, either as an advanced elective or maybe a graduate course. And it's generally considered to be a specialty within biology or medicine. And I think that's not right. It's not really a domain. It's not biomedicine. It is a set of related questions that apply in a lot of domains. And it's a set of methods in particular for dealing with censored data. And I will explain what that means. So it's a set of related questions, and it tends to be about events that occur, usually in time, although you can also do this in space. But we'll focus on time. And you might wonder, how long will it be until an event occurs? Or for a recurring event, how many times it might occur during an interval, or the possibility that it will never happen. And you might want to put probabilities and probability distributions on all of these things. The other kinds of questions that you can answer are, when is an event most likely to happen? And we're going to describe that with a hazard rate, which is the likelihood of an event. And what are the factors that might make events more or less likely? So if you're thinking about medicine, for example, what are the factors that might contribute to a longer or shorter survival time? But this is not just biomedicine. In fact, survival analysis is the name in biomedicine, but in other fields, it just goes by different names. So in engineering, it's reliability theory. In economics, duration modeling. In sociology, event history analysis. And it comes up in business as well. There are a lot of models of customer behavior. For example, a churn model would describe the time until a customer might leave and no longer be your customer or might return. And there are recurring models that are called the buy till you die models that are also based in survival analysis. So I claim that this is a useful thing. The other question that I got on Twitter is, will we use a package like Lifelines or actually implement the algorithm during the session? And the answer is both. So this is the outline for the talk. We're going to start out with Kaplan-Meier estimation, which is one of the fundamental tools of survival analysis. And then we'll switch over to using a Python module called Lifelines, which is a very nice library written by Cameron Davidson-Pilon, who has pulled together a lot of really good methods for survival analysis and also some really nice documentation. So this is going to be my recommendation after this workshop. If you want to learn more, that will be your next stop. And I'll have some links for you at the end. So that's the outline. I'm going to start by describing survival and hazard functions using a simple example. As I said, Kaplan-Meier estimation, and then lifelines. Let me present a motivating example at a high level, and then we'll get down into the details. This is from a talk that I did in 2015 that was called "Will Millennials Ever Get Married?" which is a deliberately provocative title. I'm not really making fun of millennials. If you're curious about this topic, there's a link here, which goes to my blog, which is called Probably Overthinking It. And I wrote an update on this article using new data that was released in 2020. This is from the National Survey of Family Growth. This is run by the National Center for Health Statistics, which is part of the CDC. And as I said, the 2019 data was released in 2020. And what I studied was the time until first marriage for both men and women, grouped by decade of birth, so that we can see generational changes. And this is one of the figures that I generated. These show survival curves, where survival here means time until first marriage. What age were the respondents when they first got married? And this is broken up by decade of birth. So at the bottom of the graph, for example, that purple line shows for women born in the 1940s, and we can pick a point on this curve. What it shows is the percentage who had never married, that is to say that they have survived without being married at a given age. So at age 20, oops, let me back up. At age 20, women who were born in the 1940s, about 50% of them had been married. So you can read the median off this graph. 50% were married before age 20. If you take a vertical slice out of this graph, so this dashed line is at age 28. And what this shows is that for women who were born in the 1940s, it looks like only about 15% of them were unmarried at age 28. And that is to say, the vast majority of them had been married before that age. But that has been changing from one generation to another quite dramatically. So for women, let's pick the blue line here. That's for women born in the 1960s. At age 28, it looks like there were still about 30 or 35% of them who had never been married. And if we now get to the most recent generation that we have data for, women who are born in the 1990s, we only have data for them that goes up to about age 28. And at age 28, it looks like about 75% of them are unmarried. So these are pretty dramatic generational changes. This is the same graph for men. The data don't go back quite so far in time because this survey didn't start collecting data for men until later. But we have data again for men who were born in the 1990s. And again, we see the same kind of generational change, but not quite as dramatic. So that's an example of survival analysis. And in particular, the graphical representation there is the survival curve. It shows the fraction of people who have survived up to or a particular point in time. Now, here's the challenge with working with data like this. At any point in time, if you go out and do a survey and you observe a cohort of people, you'll find that some are married and some are unmarried. For the ones who are married, you know their time until event, you know their duration, because you know when they were born and you know when they were married. If someone has not married yet, you don't know when they will get married in the future, but you can put a lower bound on it. So if they're 25 years old now, you can say, okay, well, I know that they will not get married prior to age 25, but they might get married after age 25. So the goal of this analysis is to take these two kinds of data and combine them into a single estimate for the distribution. This problem is called censored data. If you interview someone and they have not been married yet, it is as if the future data has been removed. You are not allowed to know things about the future. And so metaphorically, at least, we call that censored data. In this particular example, it is right censored, which means that it's the right-hand side of the timeline that is getting cut off. So here's our goal. We're going to develop ways of describing survival in terms of survival curves and hazard curves, which I'll define in a minute, and ways of working with censored data of this kind. So we will get to it and dive into the first notebook. If you are following along in the slides, there will be a link. And if you go back to the homepage, there will be a link. I'll give you a quick outline of what we're going to do. In the first notebook, we're going to consider the simpler case where we have a representative sample of lifetimes. That is to say, for notebook 1, there is no censoring. We have a complete data set. And in that case, we're going to compute a probability mass function, a cumulative distribution function, a survival function, and a hazard function. So I'm going to define all of those things and show you how we're going to compute them. And then in notebook 2, we will do the more difficult problem of dealing with censorship, or censoring, I should say. Okay, if you're following in the slides, there's a link there that goes to the notebook. If you click on that, it should run on Colab. If you're not familiar with Colab, I'll give you a couple of tips in just a second. But I also want to say that if you go back to the main homepage for the workshop, the same link is here. This will open the notebook on Colab. Now, you have an option, which is if you want to follow along with me, I will demonstrate some things by typing them, and you can type along as well. And I think that this is a really good way to learn because it will keep you engaged, and you are less likely to, you're more likely to remember things and less likely to tune out. However, if that doesn't work for you, if it's not a good way to work and you prefer not to do it, you have the option here. You can click and get the complete notebook that has everything that's already filled in. So it's up to you, but I do recommend that you play along and type things as we go. So let's get into the notebook. So this is a Jupyter notebook running on Colab. Colab is a service provided by Google that lets me upload a notebook and then anybody can run the notebook. What you are currently looking at is a copy of the notebook that has been copied from my GitHub repository. So the first thing I want to tell you is that you can do anything you want to this notebook. It will have no effect on me. So don't worry about breaking anything. It's totally fine. However, this notebook is running in a safe mode where it's not really saving your work. So what you might want to do is come here to the top middle of the page. There's a button that says copy to drive. And if you do that, it will make a copy of this notebook and put it in your Google Drive, assuming that you have one. And then any work that you do during this workshop will be saved and you'll be able to come back to it. In the worst case, if you do lose it, you can pick up the complete notebook that I was just showing. Okay, here's the other thing to know about the notebook. It contains both text cells and code cells. So the first few are text that introduces the topic and introduces the first data set that we're working with. You can use the up and down arrows to move between cells. You can also hold down the shift button and press enter, and that will have the effect of executing the current cell and then moving down to the next one. So I'm going to give myself a little bit more vertical space to work with here, and I'll introduce the first data set that we'll use, which is the lifetime of light bulbs that are on continuously. And this was an actual experiment that someone did. They got 50 light bulbs, plugged them all in, and ran them until they expired. What they did was they checked back every 12 hours and counted the number of light bulbs that had gone out since the previous visit. They recorded the data and it's available on GitHub. If you execute a couple more cells, when you get to the first cell that contains code, you will get this warning window that tells you that this code was not written by Google, and so it's not their responsibility, and that's fine. You can run it anyway. This is running on the cloud. It has very limited ability to do harm to anything. So it's pretty safe. And what the first cell does is downloads the data file. And if that worked, you should see a message that says that lamps.csv has been downloaded and saved. And then the next cell here imports the libraries that we're going to use, which are Pandas and NumPy and PyPlot. And if you run the next cell, it will read the file and put it into a Pandas data frame. So I'm going to pause there and give you all a chance to catch up and get the notebook running. If you have any technical problems, you can either speak up now or put a question into Slack. And I'm going to slide away for just a second and check the Slack channel and see how things are going. Okay, looks good so far. I will go on. So we have the data in hand, and the first thing that I want to do is describe a probability mass function that is the possible ages, like how many hours each light bulb might last, and the probability that a light bulb will expire at that number of hours. And this data is available in the data frame if you select df bracket f. So that's the column in the data frame named F, and what it contains is the number of light bulbs that had expired at each time step in this sequence. And what I want to do is make a new Pandas series that contains both this data, which is the number of failures, and column H, which is the number of hours. And I'm going to do that by creating a pandas.series. Using this as the data, and I'm going to extract the values. And then for the index, I'm going to use the other column, which is df bracket h. If you are not familiar with pandas, let me give you a brief introduction. The series object is a sequence of values that also contains an index. So it represents the correspondence between the index and the values. And in this case, the index consists of the number of hours that the experiment ran for. And the values in the right-hand column are the number of failures, the number of light bulbs that expired at that time. So I'm going to take this object and assign it to a variable named PMF. And I'm going to do one other thing, which is I'm going to give the PMF.index a name. And I'm going to call it T, just to be consistent with my notation going forward. So now if I display this PMF object, let me just show the first few lines using head. If I display the object, what I see on the left-hand side is the index, which is called T, and on the right-hand side, the values, which are the expiration dates, the times when the light bulbs failed. Now, notice that the failures are integers, they're counts. This is the number of light bulbs that failed. We can think of this thing as being a distribution, but normally we would make the distribution add up to 1 so that these values behave like probabilities. And we'll do that by normalizing the PMF by dividing through by the sum. So if I add them up, that'll be the total number of light bulbs, which happens to be 50. And if I divide through, the results are now normalized so that the values are probabilities. And if we look at the first few values, what this says is that about 4% of the light bulbs expired at hour number 840, about 2% expired at 852, and so on. So that's what a PMF is. A PMF is a mapping from possible outcomes to probabilities. In this case, the outcomes are the number of hours, and the probabilities are telling us what fraction of light bulbs would expire at a particular time. The PMF, one of the things that you can do with a PMF is look up a particular time and get the corresponding probability. So if you use the square brackets, PMF bracket 840 will tell you the probability that's associated with hour 840, and we've already seen that that's about 4%. I'm going to show one other example, which is not super interesting, but it will make a little bit more sense when we get to the next section. We can also look up, for example, 1524, and it turns out that about 6% of the light bulbs expired after 1,524 hours. Okay. I have a couple of functions here that I'm going to use to display results. I have a function called decorate that's just a convenient way to put labels on the axes. The details of that are not super important, but this is a way to visualize what the PMF looks like. It's just taking the data from that Pandas series and plotting it as a line plot. Now, honestly, this is not the best visualization of this data, but it shows one of the things about PMFs that is not ideal, which is that they tend to be noisy in a way that makes it difficult to see exactly what's going on. So we do have a sense from looking at this that most of the lifetimes are between roughly 1,000 and 2,000 hours. But from this figure alone, we don't get a very clear picture of what this distribution looks like. We're going to do a lot better by using a CDF, and that's where we're headed next. So in the next section, I'm going to take this PMF and compute its CDF, and I'll explain what that is if you're not familiar with them. I'll use this little triangle widget to open up the next section. However, before I go on, I'm going to pause again to check on Slack, and if you have any questions that you're stuck on, feel free to unmute and ask, and then we'll go on. Okay, looks good. I heard from at least one person that says that the Colab notebook is working. I saw one question that asked about continuous versus discrete representations of these distributions for survival analysis. Everything that I'm going to do is discrete, in part because it's coming from these relatively small data sets. But yes, there is a continuous version of everything that we're currently doing. My intention here is by showing you the discrete version, I think, in my opinion, it's easier to understand the concepts. And then when you go to the continuous version, the math becomes just a little bit more advanced. You've got, integrals and derivatives, for example. But if you understand the concepts, I think it's not too much more difficult. So let's move on. We've got a distribution and we've represented it with a PMF. The next thing we'll do is also represent it with a CDF. And in terms of discrete mathematics, it is the the cumulative sum of the probabilities that are in the PMF. So I'm going to create a new CDF thing, which is the PMF.cumulative sum. And that is a Pandas function that computes cumulative sums. And if we look at the head, the first few values that are in the CDF, we can see that these values, 0.04, 0.06, 0.08, 0.10, are the cumulative sums from the PMF. So 4, 2, 2, 2, if you add it up, becomes 4, 6, 8, 10. And that's what we have in the CDF. So it doesn't seem like we've changed much here, but this does two things for us. And one is that we can quickly compute the fraction of light bulbs that expired at or before any particular time. So again, we can use the square brackets to look up a timestamp. And what it says is that 4% of the light bulbs expired at or before 840 hours. That's not too interesting. We kind of knew that. But we can also put in a value like 1524, and it'll tell us that 60% of the light bulbs expired at or before 1524 hours. So that's one thing the CDF does. What it's computing there is a percentile. It's telling us that the 60th percentile is 1524. And the other thing that the CDF does is it gives us a way to visualize the distribution that is not as noisy as the PMF. And so what we see here is very roughly a sigmoid kind of shape that says that there are very few light bulbs that expire before 1,000 hours. The great majority of them, if we read off 1,000 on the graph and come up to here, it looks like fewer than 20% of the light bulbs die before 1,000 hours. However, very few of them exceed 2,000. If we come up here and read off 2,000, what that's saying is that, let's say 95% of the light bulbs have expired before 2,000 hours. And in between, it's a straight-ish line. So we could say that very approximately, this is a uniform distribution from about 1,000 to about 2,000. Okay. So far, that might have been familiar to you. If you've taken a statistics class, you probably know about PMFs and CDFs. You might not know about survival curves or survival functions. The mathematics of it couldn't be simpler. The survival function is just the complement of the CDF. So if someone asks you for a survival function, you can just compute 1 minus the CDF. And if you display it, survival.head. This is the fraction of light bulbs that exceed a given time t. So what this is saying is that 100% of the light bulbs, the fraction is 1.0, 100% of the light bulbs lasted longer than 0 hours, I should hope. 96% of them lasted longer than 840 hours, and so on. And again, if you like, you can use the square brackets to look up a particular value, like my favorite, 1524, and that'll confirm that it is the complement of the CDF. So the CDF was 60%, the survival function is 40%. And if you plot both the survival function and the CDF, you can visually see that they are complements of each other. The difference is that the survival function starts at 100% and comes down. The CDF goes the other direction. So nothing super profound going on here. The only reason that survival functions exist is partly convention, that in the domains where we do survival analysis, this is the conventional way of showing distributions. However, it is also a step toward the hazard function. So if you've got survival functions, it is one step easier to compute the hazard function, which is what we'll do next. But I will pause there. Once again, I want to check Slack for questions, and feel free to unmute and ask if you've got something. Yes, I see a question on Slack that says the PMF is not the cumulative probability, it is the instantaneous probability of failure at a point in time. And that's correct. Now, in this particular experiment, instantaneous means these little 12-hour windows during where they checked the light bulbs. So in that sense, the data have been discretized by the nature of the experiment. But yes, so the PMF is an instantaneous thing. The CDF is the cumulative probability of dying before a particular time. The survival function is the probability of dying after a particular time. And that's what gets us to the survival rate, the hazard function. The hazard rate is the fraction of light bulbs that survive until time t and then fail at time t. So you can think of it as the instantaneous danger, like how much danger are you in? If it's hour number 1524, what's the probability that a light bulb that has survived up until this point will expire at exactly that point? And in order to compute this, we need both the PMF and the survival function, because the PMF tells us what fraction of bulbs expired at t, and we will use the survival function to compute the fraction that were alive at t. And it's going to be the sum of two parts. If we add the PMF and the survival function, that will tell us how many light bulbs were still burning at time t. The PMF tells us how many of them expired at time t. And the ratio of those two things is the hazard rate. So I've said it in words. Let me show it to you in code. It's almost simpler in code. It is the PMF divided by the sum of the PMF and the survival function. And just to say it one more time, the denominator here is the number of light bulbs that were still burning at time t, and the PMF is the fraction that expired at exactly t. And so that what we are interested in is the ratio of those things. And here's what the head of that looks like. So taking the first row, or the first interesting row, what this is saying is, of all the light bulbs that survived until hour number 840, 4% of them died at that point. And maybe taking this one, this says that of all the light bulbs that survived until 960, about 2%, a little bit more, expired at that point. Here's what this function looks like. So this is a function of lifetime, again, hours from 0 up to about 2,500. And this is the probability that a light bulb will die at this time, given that it has survived up until this time. And that's maybe another way of thinking about it, is it's like a conditional probability. So looking at 1,500, for example, this is, given that you have survived until 1,500, what's the probability that you will expire at 1,500? Now, the hazard function has the same problem that the PMF has, which is it's based on discrete data and it tends to be pretty noisy. And so not easy to see what the shape of the curve looks like. However, there's a little bit of a trick that people do, which is to plot the cumulative hazard function. And here's what that looks like. I'm using the cumulative sum function again. So this is the same way that we computed the CDF, and plotting the cumulative hazard. And it has the same effect. It is smoothing out the noise and showing a little bit more clearly what's happening where. However, the vertical axis now is a little bit hard to interpret because this is the sum of a rate, which in mathematical terms doesn't really mean very much. So don't pay too much attention to the values on the y-axis. The 4, for example, doesn't really tell us much of anything. However, we can tell from looking at this curve where it's steep and where it's shallow. Because when it's steep, that means that a lot of light bulbs were dying in that range. That means that the hazard function is high. And where the slope here is low, that means that the hazard function is low. So if we look at this part of the curve from about 1,000 hours to 2,000 hours, it has positive curvature. It has increasing slope. And what that tells us is that it is an increasing hazard function. So it starts out slow, meaning that the hazard is relatively low between 1,000 and 1,500 hours. And then it is steep here, and that means that the hazard function is higher between 1,500 and 2,000 hours. So that's the hazard function and the cumulative hazard function. Let me again pause. I'm going to check Slack, and feel free to unmute if you have a question.
So quick one. So hazard function, is that on, in general, like the average of all the observations, or is it something else? Because I scroll down slightly and you're doing it for each observation as well.
Yes. Are you talking about the next section here where I'm resampling?
Possibly, yeah.
Okay, let me get to that in just a second. And I think I'm not positive I understand the question, but let me say something and see if it helps, which is this curve is based on the entire data set. So when I'm doing all of these Pandas operations, it's doing them element-wise on the whole PMF. So
Right. Yeah.
it's
Okay.
computing for the whole data set at once. Did that answer your question?
Yeah. Yeah. I think I was reading too quickly and not really understanding.
Gotcha.
But yeah,
Okay.
sounds good. Cheers.
And I am probably going fast, and I hope things are making sense. We are going to go for just a couple more minutes to finish this notebook, and then we're going to take a break for 5 minutes. And I hope that will give you a chance to take a breath, look at what we've done so far, and ask more questions if you have them. Okay, at this point, we have computed all the things that we're going to compute. I'm going to do one thing in the next section, which is to think about what parts of this curve are reliable and which parts are probably like statistically noisy. And one way to think about this, if we look at the left-hand side of this curve, nearly all of the light bulbs were still burning at 500 hours. And what that means is that the sample size here is about 50. Almost 50 light bulbs were worn. And that means that it's probably pretty reliable. If we go to the other end of the thing, this data point, all the way at the end, is based on a single light bulb that happened to last for more than 2,500 hours. So in some sense, the sample size on the right-hand part of this curve is 1, which means that from a statistical point of view, it's not very reliable. And that's one of the things to look at in the next section, is to get a sense of how much variability there is in these functions because of random sampling. And I'm going to do this by a resampling process. If you're not familiar with resampling, this might make your head hurt just a little bit. But here's what I'm going to do. I'm going to take the actual data, and I'm going to use kernel density estimation to make a model for the distribution. So this is like a smooth version of the distribution. And then I'm going to use the resample function to draw a new synthetic sample from that model. So again, I'm using the data to build a model, and then I'm using the model to generate lots of synthetic data sets. And you can think of these as like alternate universes. This is what the data set could have been if I had sampled it differently, if I had got a different set of 50 light bulbs. And what I'm going to do for each synthetic data set, I'm going to do 100 fake data sets. And for each one, I'm going to do the complete computation that we have done so far. That's what this function does. I have a function here that is called make hazard. And what it does is it computes the PMF of the synthetic sample, the fake data. Then it computes the CDF, the survival function, and the hazard. So this is kind of like everything we've done so far, stuffed into one function. And it returns all 4 of them. So what this loop does, let's take a look at it. I'm going to do that 100 times. Oh, go ahead. I thought I heard a question. Yes, go ahead, please. Okay, it might have been. If you want to put something in the Slack, we can do that too. So again, just to explain what this is doing, I'm going to run it 100 times, contrary to what the comment says. Run it 100 times, generate a fake sample, compute all of the functions, compute the survival function, and plot it. So I'm going to plot 100 gray lines, and then the blue line is the actual data. And you can think of this as a visual confidence interval that's telling you how much different the data could have been if I ran the same experiment again under the assumptions of my model. And this gives us a sense of how statistically precise the estimate is for this survival function. And what it's showing is that it's reasonably good over the whole range of the survival function. If we do exactly the same thing for the hazard function, it answers the question that I posed a minute ago, which is what parts of this curve are reliable and what parts are more statistically noisy. And it pretty much goes from left to right. So this is like a cone of uncertainty that gets bigger, because as we move to the right-hand side, we're losing sample size. And by the time we get to the last few data points, it is statistically very noisy. So that is the end of the first notebook. I'm going to do a quick review and then we will take our break. But let me, before I leave the notebook, any questions that I should answer here?
Yeah, I do have two.
Yes, go ahead.
Okay, so the first one was already posted on Slack, and it is when you built the basically the hazard function, and you show the head of the data frame, you refer to the point that were sampled as percentages. So should we assume that the hazard function is a probability distribution? Like
good question. Yes and no. So it is not a distribution function because those rates do not add up to 1.
Okay.
So each of them is a different rate. And in fact, we know what they add up to because that's what the cumulative hazard function is. So it turns out in this example that they add up to 4. And that doesn't mean anything except that it's not 1. And what this is saying is each rate is a percentage. It is the percentage of light bulbs that live up until time t and die at time t. Oh, let me say that a little bit differently. It is the fraction of all the light bulbs that survive until t. It is the fraction that die at t. So you can think of it as a probability, but the hazard function is not a probability distribution because it doesn't add up to 1.
Okay, cool. Thank you. And
Sure. Go ahead.
The second question is instead of related to the kernel density estimate, and it is a side of practical purposes. Why choosing a Gaussian KDE? Does this put any assumption on the distribution of the data? Is it related or just because?
Right. I used KDE. You're right that it makes an assumption. It does not assume that the distribution is Gaussian. It only assumes that the distribution is somewhat smooth. And in this case, I think it's a reasonable assumption. So I think KDE is making a very weak constraint on the model.
Okay, so that entails also that we could use basically any other density estimate, like even a Poisson or?
Yes, probably. For what I'm doing here, the particular choice of the model is not going to have a strong effect. I could even just do discrete resampling. I could draw a sample from the original data without doing any smoothing at all. And that would work too.
Okay, cool. Thank you, Doc.
Sure. Good. All right. I'm going to jump back to the slides for a second. And because I just wanted to show this figure. This is a summary of everything that we just did. We started with a sample. We computed the PMF, although in the light bulb example, they had sort of already computed it for us. We computed the PMF. We did the cumulative sum to get the CDF. We did the complement to get the survival function. And then to get the hazard function, it's basically division because we're computing a rate. And then we also computed the cumulative hazard as a way of visualizing the hazard rate. And that is the first half. So congratulations, you have survived. I'll say one quick thing, which is that all of these representations are equivalent in the sense that if you are given any of them, you can compute all of the others. Now, the reason that it's useful to have different distributions is that they can answer different questions. And we showed that in the notebook. I review it a little bit here in the slides, but I think I won't present these. If you'd like, you could read that during the break and let me know if you have questions. because I do want to make sure that we take a break. So we'll come back in 5 minutes when the dancing animals have stopped dancing. That's still a little bit too loud.
Alan, I wanted to let you know you're an unpopular name in my house. I just had my first child, and yes. I was reading your Think Stats while my partner was waiting to go into labor, and she was very upset that I told her at week 39 there was a 50% chance that the child would be born that week, and at week 40 it wouldn't increase; it would still be 50%.
That's correct. That is the cruelest curve in survival analysis.
Yeah. And so she told me to stop reading Think Stats and and start doing things to help the baby come out.
Well, congratulations.
Yeah, thanks. Did come.
At what week?
Week 40, yeah, halfway through.
40.
Yeah.
Yep, that's long.
Yeah. Well, there was a 50% chance. Oh no, 50% chance once we'd arrived at 40. Of course, there was.
Yes.
Yeah. Yeah.
Yes, my second child was several weeks late and eventually required a little bit of incentive. Okay, I think the dancing animals are done. And let us get back to it. So just again, to summarize what we have so far, we have several ways to represent a distribution. And we know how to compute them going in the forward direction. And now here's the key to the second part, which is, so all of this, what we've done so far, depends on having a representative sample, meaning, among other things, no censoring. If we have censored data, we're going to use Kaplan-Meier estimation. This is one of several methods, but it is one that I think is the foundation. It gives you the clearest picture of what's going on. The key idea of Kaplan-Meier estimation is that instead of starting from the PMF and going forward, we are going to start from the hazard function and go backward. So here's the forward direction. This is what we just did in notebook 1. Here is the reverse direction. This is what we're going to do in notebook 2. We'll start with a sample and directly estimate the hazard function. And then from there, we will go backwards to do the survival, CDF, and PMF curves. That is the plan, and that is the outline. If you follow this link, you'll get into notebook 2. Or again, if you go back to the homepage for the workshop, you can also follow the link from here. And just as a reminder, if at any point you get lost or you don't want to play along anymore, you can go to the complete notebook and view it on NB Viewer. But let's jump into notebook 2. So this is the notebook on Kaplan-Meier estimation. And again, when you start the notebook, the first code cell that you run is going to give you a warning. We're going to import the libraries. Now, for this example, I'm going to use completely fabricated data. I'm just going to make up some numbers, but to give them some context, you could imagine an experiment where you want to know how long it takes for a dog to get adopted from a shelter. So if you have an observation window of 10 weeks, you might record the arrival time for every dog that arrives during your observation window and the adoption time for the dogs that were adopted. But at the end of your observation window, there might be some dogs who are still in the shelter. They haven't been adopted yet. You know how long they've been there, but you don't know how long it will be until they're adopted. So those cases will be right censored. And here's how I'm going to represent that. I'm going to create a data frame with 3 columns. It has the start time, the end time, and the status. So start time is when the dog arrived at the shelter. End is when the dog was either adopted, or this is how many weeks the dog had been there at the end of the observation period. And the status column indicates which one it is. So if status equals 1, that means that the dog was adopted. If status equals 2, that means that the dog was still at the shelter at the end of the observation period. That's the data frame. And I've got a function here. If you enjoy matplotlib, you might like the details, but what it does is it generates a plot that looks like this. And these are called lifelines. And they represent, in this case, the life of the dog, meaning from the time that it arrives in the shelter until the time that it leaves the shelter. And again, there are 2 kinds of cases. The orange lines end with a dot, and that means an adoption. And the blue lines end at the end of the observation window. And so that means that that dog had not been adopted at the time that we stopped watching. The vertical axis here is just an index for dog number 0, dog number 1, dog number 2. And so if you read this, you would say, okay, dog number 0 arrived during week 0 and was adopted during week 5. And if you go down, dog number 3 arrived at week 2, and it was still in the shelter at the end of week 9, which was the end of the observation. So here's what we're going to do. We want to estimate the survival curve, and we're going to do this by computing the hazard function. And let me show you how we're going to do that. We're going to sneak up on it gradually. I just need to get my notes. All right. The first thing I'm going to do is separate out what I'm going to call the complete cases from the incomplete cases. So complete means that we know the adoption time, and incomplete means we don't because the dog was still in the shelter. So I'm going to pull out complete, and it's going to be the duration. And let me back up. I think I need to compute duration. All right. So I'm going to pull out the durations. And this will be the difference between the two columns. So I've got my observations, and I have the end minus the observed start. So that'll be my duration. And I'm going to display that. Okay. So the duration for dog 0 was 5 weeks. The duration for dog 1 was 1 week, and so on. Now I want to pull out the complete ones. So complete is going to be the durations, and as an index, I'm going to use the observation that the status is equal to 1. So this term, that will be true for the dogs that are complete when status is 1, and it'll select only those durations. So complete will be a subset of the durations 5, 1, 4, and 2. And ongoing, those are my incomplete cases, will be the duration in the case where the status is 0. And we can see what those values are. Okay, so I've partitioned the data set into two chunks, the durations for the complete observations and the incomplete observations. That was a lot of typing, so I'm going to leave that up on the screen for just a second and make sure that you have a chance to catch up. Oh, and one other thing I didn't mention, again, if you want to make sure that your changes are being saved, you might want to press that Save to Drive button up at the top. Okay. So I've separated out my complete cases from my ongoing cases. And now I'm going to make a different PMF for each of them. Right. Okay. Sorry, I've messed up a little bit here, and so I need us to go backwards. I have put the wrong code into the wrong section. So some of this is exactly what we need. We do need duration. I'm going to take this code and copy it into the next section, and we'll come back to it in a minute. And I'm going to delete this code for a minute because I just did the wrong thing here. So sorry, let me back up. There is another key step here that I've skipped. So let me be a little bit more careful. I was rushing and messed things up. There are two key ideas that we need to fix. And one of them is all of these dogs arrived and departed at different times. In order to make them more comparable to each other, we're going to take all of these lifelines and shift them to the left as if all of the dogs had arrived during week 0. And this isn't going to change any of the durations. It's just going to line them up so that rather than using clock time, like what week it is of the year, we're going to use relative time, like how long have they been in the shelter. And I'm going to do that by making a copy of the observation notebook data frame. So I'm going to make a copy of this, and I'm going to change all of the start, change all of the start column to 0. So it's as if all the dogs arrived during week 0, and all of the end durations, all of the end times are equal to the durations. Okay. And we can see what that looks like. Shifted bracket, dot head. Yeah, shifted. All right. So again, I'll give you a second to catch up with the typing. I computed the duration for each dog. I created a copy of the observation data frame. I shifted it so all the start times are 0. All of the end times are equal to the durations, and the status column is the same. And now if you plot lifelines, which is the same function that we used before, and you plot the shifted values, it should look pretty much the same, except that all the lifelines are now starting at week 0. So I'll put that code up and give you a second to type. Any questions on this? Again, I'm sorry about the confusion. So that's the first key idea, is to take all the lifelines and shift them so they start at 0. And then the second key idea is to compute the hazard rate by considering how many dogs were there that could have been adopted at each timestamp, and how many of them actually were adopted at each timestamp. And the idea here is at risk. We would say that a dog is at risk if it was available for adoption during a particular time. So if we look at the figure, starting at week 0, there were 7 dogs at week 0 that could have been adopted, and none of them were adopted instantly. So there are no dots at week 0. If you look at the next vertical column in this figure, starting here, there are still 7 dogs available, and one of them is adopted. So the hazard rate at time 1 is 1 out of 7. If you look at the next timestamp, timestamp 2, now there are only 6 dogs that were still observable during week 2, and one of them was adopted. So the hazard rate at week 2 is 1 out of 6. And that's how we're going to get the hazard rate out of this diagram, by computing the number of dogs who were at risk during each time step and the number who were actually adopted during each time step.
I got a quick question if you...
Yes, please.
I posted in the Slack, but I was curious, in order to shift the data and perform this analysis, it sounds like we're making the assumption that adoption of dogs is not impacted by effects like seasonality. Are there other sorts of assumptions that we're making about this data, or is that a true assessment of this analysis?
That is correct. That's a great point, and thank you for making it. You're absolutely right. So we're assuming that the actual time in the world doesn't matter, and that means that adoption rates are considered to be constant in this model. That they might depend on how long the dog has been in the shelter, but they don't depend on what the calendar date is.
So does that mean that seasonal, so is there a version of survival analysis that takes into effect things like seasonality?
Yes, absolutely.
Okay.
And that's, we're not going to do regression models today, but there are regression models that work for this kind of data. And I'll point you to them as a resource, but that's an example where that would let you explore whether there are external factors that affect the hazard rate, and a seasonal effect, or any kind of external time effect would be you could include that in the model.
Okay, all right. Thank you very much.
Sure. Okay. All right, now we're ready to do what I started to do before, which is to break the data set up into 2 parts for the complete and incomplete observations. We started to do this a minute ago, so you might already have this code, but I'll just bring it up to date. So the ongoing will be the ones where the status is equal to 0. There are 4 dogs that were observed being adopted and 3 that were still in the shelter at the end. And I've got this make PMF function that's going to compute separate PMFs for the 2 cases. So I'll have a PMF for the complete cases by running make PMF on the complete data, and a PMF ongoing using make PMF for the ongoing data. And I think they're not particularly interesting looking PMFs. Now, one note, I'm calling these things PMFs, although for this example, I'm not going to normalize them. I could, and the whole computation would work if I normalize them, it would be the same. I just think it's a little bit easier to keep them as counts, because that's going to let me, I don't know, I just think it's easier to keep track of what's going on. Now, I've got these 2 PMFs. I'm going to put them together into a data frame, because this is going to let us see each step of the computation as it goes along. So I'm going to create a dictionary, and I'm going to put into the dictionary the 2 PMFs that I just created. So PMF complete equals PMF complete, and PMF ongoing equals PMF ongoing. The reason I'm making a dictionary is that it's a convenient way to make a data frame, but I need an index. So the index is going to be the union of the 2 indices. PMF complete dot union PMF ongoing, and I'm going to extract the index from each one. Now, this is a little bit of Pandas magic. So if you're not familiar with Pandas and indices, this might be a little weird, but let me show you the result, and then I think the process will make more sense. I'm going to create a data frame called pd.dataframe that has the dictionary as the values and that index that I just created as the index. And I'll display it. And this has allowed me to put the 2 PMFs into the same data frame and to line them up so that the index, the column on the left-hand side, these are the week numbers. This is telling me that during week 1, there was 1 dog that was adopted. During week 2, there was 1 dog that was adopted and 1 dog that was observed at week 2 and then left the observation window. And I'm doing all of this because what this is going to allow me to do is compute the number of dogs who were at risk during each week and the fraction of them that were adopted. Now, I'm going to do one more thing, which is a fill-na, which is I'm going to replace the not a number values with 0. And that is that. So let me put that code up on the screen, give you all a chance to catch up. I'm going to check Slack, and then we'll go on.
I have a question, if I may.
Yeah, go ahead, please.
Yeah, this might be sort of similar to the seasonality assumption earlier on, but are we also assuming that each dog's process is probabilistically independent from every other dog's process? Like, I don't know, if a shelter gets super full, either like a lower probability or higher probability than that a dog gets adopted, for example.
Right. Yes, this model is making the assumption that the dogs don't affect each other. So, right, I think you just gave an example where, yeah, if there are a lot of dogs, then the probability for each dog might be a little bit lower. And so that's, in this example, the model might not be completely realistic.
Okay. Thank you.
Okay. So I don't want to get too bogged down in the computation here. Where we're headed again is we're going to compute the number of dogs at risk. And in order to do that, I'm also going to compute the survival functions. And again, what I'm going to do is compute the CDF, which is the cumulative sum of the PMF, and also the complement. So once I've got the CDF, I compute the complement, and that's the survival. And I'm going to add this as an additional column in the table. So df bracket, I'm going to call it s_complete. This will be the survival function for the complete cases, is going to be the make serve function, passing in the PMF that we computed from the table. So df PMF complete. And make sure that you get the version that comes from the table, because it has been stretched a little bit because of the new index. And if you visualize that table, you can see what we're doing here. So we're adding a new column to the table that is the survival function for the complete cases. And I will also add the survival function for the ongoing cases. Now, why is this useful? If I add up these 4 columns, that is the number of dogs who are at risk. Because the number of dogs who could be adopted during a given week is the sum of all the ones that survived to that point and got adopted, all the ones that survived at that point and left the observation window, all the ones that survived past that point, which is the survival curve, and were either adopted or not. So the sum of these 4 columns is the number of dogs who were at risk. And so I can add that df bracket at risk is df.sum. And I'm going to sum along the horizontal axis, which is axis 1. And, oh rats, I spelled it wrong. I'm gonna leave it spelled wrong rather than add 2 columns, but you should spell it right. Nah, I'm gonna fix it. Hang on. At risk. Okay, and now I'm gonna delete df bracket r. Let's see if I've got it fixed. There we go. All right. Now, we know how many dogs were at risk during each week. And
sorry, Alan.
Oh, yeah, it's something.
I think the sum doesn't add up now.
No, it sure
correctly.
doesn't. Yes, you are correct. What has happened there? Let me.
I think you have to delete the column before you sum.
Yes, I'm going to just back up and create the data frame again from the top. But yes, you're right. I had an extra column in there, and then I computed the sum several times. And so I ended up with extra stuff. There we go. That's better. All right. Now I know how many dogs were at risk during each week. And PMF complete is the number that were adopted during each week. And so the hazard, df bracket hazard, is the ratio of those 2 things. It's df bracket PMF complete divided by df bracket at risk. And I'll display it. There we go. So one more time, I'll pause for just a second, give you a chance to catch up. I'll check Slack. Looks good. All right. And just a reminder where we are here, we're doing this. So we've just done the first step, which is to take the sample and compute the hazard function. That was the hard part. And everything else now is just to take the things that we did before and do them in the opposite direction. So given the hazard function, we're going to compute the survival function, the CDF, and the PMF. And that's what's in the next section. So let me show you the computation, and then I'll explain why it is what it is. df bracket serve, the survival function, is going to be 1 minus the hazard function. So the hazard function tells you, if I'm alive at time t, what's the probability of dying at time t, or in this case, adoption? If I'm still in the kennel at time t, what's the probability of being adopted? So the complement is the probability of not being adopted. So if I'm not adopted at time 0, and I'm not adopted at time 1, and I'm not adopted at time 2, the probability is the product of each of those. And so if I take this hazard function, compute the complement, and then compute the cumulative product, that will be the survival function. That is my chance of making it past all of these gates. So you can think of each of them as being a gate where I have some probability of surviving, and the cumulative product is the probability of surviving past all the gates. Once I have the survival function, I can compute the CDF, which is the complement of the survival function, and display the data frame. And once I have the CDF, I can make the PMF. Now remember that the CDF is the cumulative sum. So to go in the other direction, I'm going to use diff. And I'm going to use np.diff. And this is a little bit of a hack. Rather than using pandas, I'm using np. And the reason is that it does something for me. I can compute the difference of the CDF, and I can prepend a 0. And that causes it to do the computation correctly. I won't belabor the detail there. And that's it. That's the whole process. So we did a fair amount of work to get to at risk. But once we had that, we computed the hazard, the survival, the CDF, and the PMF. Now, how are we doing out there?
Is the prepend something like fill NA 0? If you would do it with diff on the pandas?
Yeah, so what it does is it takes the sequence and it puts a 0 at the beginning, and then it computes the diffs.
Mm-hmm.
And for this particular case, going from a CDF to a PMF, that's exactly what we want to do.
So for weeks where no dog was adopted, it just doesn't have any data, basically?
Yes, so it's treating the hazard function as kind of like a delta function, where it's 0 everywhere, and then it has values at these particular points in time.
Mm-hmm.
I'm a little bit confused about something. I may have missed something early in this Jupyter notebook.
Mm-hmm.
But why are we doing this backwards analysis instead of just repeating the same analysis we had before?
Yes. So the problem is that this only works if the sample is unbiased, meaning that it doesn't have any censoring.
I see.
So if all of the cases are complete cases, like if we follow the dogs until they're adopted, then we could do the forward process. When we have missing data, when we have the censored data, that's when we have to do this.
Okay, I see. All right, thank you.
Good. All right. The next section of the notebook, I believe we don't have to do any typing for this one, but we do have to install lifelines. So if you run this cell, it will install this library. It's pip installable, it's pure Python, so it's a pretty clean installation. And
hi, I have a question too. Hello.
Yes, go ahead, please.
In real life scenario, do you think we most often find ourselves in the censored situation? I'm thinking like a business where I've not had a chance to observe every customer for, let's say, 5 years of lifetime value.
Right.
Then I am looking at a censored set of observations and I have to predict whether this customer will last or not. So in most real world situations, would you say we are dealing with this sort of censored data?
Yes. Yeah, exactly for the reason that you just said, which is that very often what you want to do is use all the data up until the present in order to make a prediction for the next, week, month, whatever it is. And what that means is that you're almost always working with right censored data.
Got it. Thank you.
Sure. And that maybe brings you back to the beginning where we said that this is a vastly underappreciated method. And I think that's exactly the reason, which is this kind of data censorship is extremely common. Now, I'm getting close to the end of time, and I do want to make sure that we end at the correct time. So let me summarize a couple of things, and then we'll have maybe just a minute for questions. Again, we have several different ways to represent distributions, and they are equivalent in the sense that if you are given any of them, you can compute all of the others. And then the second notebook, we did Kaplan-Meier estimation, and that's the case when the data are right censored, we can estimate the hazard function and use it to compute all of the others. Now, we got the question earlier is, what if there are external factors that affect the hazard rate? And for that, you want regression methods that would allow you to estimate the hazard as a function of all of these external factors. And for that, I will point you to lifelines, which I skipped in the notebook, but you can continue that section if you go to the complete notebook. What it shows is that the Kaplan-Meier estimator that is built into lifelines computes exactly the same result that we just computed. So it works. It has a very nice section. The documentation here, I think, is very good. And in particular, the section about survival regression, that is, I believe, your next stop after this workshop. You should go read that. If you enjoyed this, you might also like ThinkStats. This is based on one of the chapters from ThinkStats. And my most recent project is the second edition of ThinkBayes, which just came out a couple of months ago. If you're interested in Bayesian statistics, you could consult that. And then last, I wanted to give you this. This is the 5 ways to get in touch with me, including my blog, which is called Probably Overthinking It. And so if you enjoyed this, you might like some of the articles there. And let me take a breath, see if you have any questions, and then we'll wrap up.
So I just have a general question, if I may. So it's been a while since I've been in a formal probability course, but at least the kind of problem this seems to tackle to me seems like it's reminiscent of the intro stochastic processes that I've seen when they first introduced it to students as a Bernoulli or Poisson processes, time until light bulb goes off, the type of things. Like what is the, I don't know, maybe like academic genealogy link or like topical overlap, or maybe comparative, kind of critical comparative idea here. How do the two spaces relate?
Right. Yes, there are lots of connections. I won't have a coherent answer off the top of my head, but let me give one example. So thinking about a Bernoulli process, for example, which is a bunch of coin tosses, where the coin tosses are independent.
Right.
There's one very simple model, like a survival model, that says, I'm going to toss coins until I get heads, and I'll record the total number of coin tosses that I needed in order to get heads. And if you do that, then the distribution of lifetimes will be, I think, geometric if it's discrete and exponential if it's continuous. And that would be analogous to a survival process where the hazard function is a constant. In other words, the probability of getting heads is the same for every coin toss. But you could also imagine a similar kind of experiment where it's a biased coin and the bias increases over time. So every time you toss heads, every time you toss the coin, the probability of heads goes up. That would be like a hazard function that's increasing, like the light bulbs. So the light bulbs had an increasing hazard function. And there are other examples in the real world where the hazard function might go down over time. Or one of the most common is a bathtub shape, which is many things are likely, like if you think manufactured parts, for example, if there's a manufacturing defect, they would tend to fail right away. And so the hazard function is high. But if you get through the initial burn-in period, then it's low for a while. And then eventually the part wears out and the hazard function increases again.
I see.
So I think that's my best attempt to create a connection between stochastic processes and this kind of survival analysis.
It's almost as if it introduces survival analysis, introduces an extra flexibility around the assumption, which is usually the assumption between Bernoulli and also Poisson processes of constant probability across time.
Right. So this models situations where the hazard function can vary in time in arbitrarily complicated ways.
I see. Okay, that's helpful. Thank you.
Good, thank you. It is exactly 1 o'clock, so I should stop on time. But if you do have other questions that I didn't answer, feel free to jump over to Slack and I'll stick around for a little bit and answer questions there. Thank you all very much. I hope it was useful to you, and feel free to be in touch if I can help with anything. Thank you. Bye-bye.
Thank you, Alan. So there's one more thing I would like to say. The session is being recorded and it would be uploaded on the website latest by today evening. So you can keep an eye on that. And the link would be on the events page, pyta.org/global2021/events, just below the Zoom link of the session. So you could just rewatch it or, again. And Alan, if you could just please upload any slides or notebooks, if you could. I think you have already did that, right? If I'm not wrong.
Yes, the landing page for the workshop has everything, and it will also have the video once the video is available.
Awesome. Yeah, so that brings us to the end of the session. Thank you, Alan, and thank you everyone for joining us today.